The plan is to go over section H in each of the books. So we'll start today with section H in graph theory, and then we'll finish the semester with section H in the combinatorics book. I thought that maybe today we can go over the answers to the exam. I'll try to read as much as possible over this weekend, so hopefully you can see the grades next week. But for now, I'll go over the questions since this is still kind of fresh in your minds, and before we move on to a different topic. So, all right. So here's the exam. All right. So let me start with the inclusion exclusion problem. Okay. So for this one, you have rearrangements of these words, these 6-letter words. So that's what I'm going to make my U for both problems, for both parts. U is going to be the rearrangements of U, V, W, X, Y, Z. And then for part A, the things that I want to avoid are having U in the first position, W in the third, Y in the fifth. So I'm gonna write my A U, A W, and A Y is the rearrangements of U, V, W, X, Y, Z, having U in the first position. So that's what I want to avoid. So
do we have to write all this stuff? Because I was worried about, I know we were supposed to explain our answers, but I was worried about if I explained too much in detail, then I would lose time on actually answering the problem.
You do need to say what your A's are, because otherwise I don't know what you're counting. But it can be less worthy, more worthy, but you do need to say what your sets are, how many, what they are.
Guess I'll get points deducted off that problem then. Because I think all I did was S0, S sub 0, S sub 1, S sub 2, and then I did equals this. Stuff like that.
Well, I'll have to see it shown, but maybe there's something there that points to the description of the sets. We'll see. So once you have your sets, U is just the rearrangements, no restrictions. So that's just permutation 6 factorial. S1 is the cardinality of AU, AW, and AY. And because we are fixing one letter in one position, then we only have to scramble the other 5. So that's 3 because it's 3 terms times 5 factorial. S2 is the intersections by pairs. And for all of them, we are fixing exactly 2 letters, and therefore we're only scramble 4 of them. But it's going to be the same for each of the terms. So this is going to be 3 choose 2, 3 times 4 factorial. And then S3, we're fixing the 3 letters, these 3 letters in their positions, and we're scrambling the other ones. We're permuting the other ones. So this is 3 factorial. And therefore, your answer is going to be that 6 factorial minus 3 times 5 factorial plus 3 times 4 factorial plus minus 3 factorial. So that's for part A. I'm going to move things down. Oops. So for part B, again, the universal set is still the same. But this time, what we want to avoid are these substrings. So AUV, ABW, and AXYZ are the rearrangements of UVWXYZ containing UVWXYZ. And so for this, give me 1 second. Oops. Okay. So for this, we have, again, S0 equals 6 factorial, but then S1 is going to change a little bit. We have different countings for the different sets. So for UV, we glue together the UV. So UV, we glue together the UV, we have W, X, Y, and Z. So this gives me 1, 2, 3, 4, 5 elements. So this is 5 factorial. For VW, we do the same. We have U, VW, X, Y, Z. So we have 1, 2, 3, 4, 5 elements again. But for AX, Y, Z, we have U, V, W, and X, Y, and Z are glued together, which gives me 4 elements. And then S2, it's AUV, AVW plus AUV, AXYZ plus AVW, AXYZ. And so in this one, we have UVWXYZ, and we're supposed to have together both UV, UV, and VW. And therefore, all of these three need to appear in that order. So this gives me 4 factorial. And then for the next one, I'm supposed to have UV together, W by itself, and then X, Y, and Z together. So this gives me 3 factorial. And for the last one, I have VW, U, VW together, X, Y, and Z together. So this gives me another 3 factorial. And then S3 is having UV, VW, and XYZ together. So again, for UV, VW, for the XYZ, they need to be together. For the UV and VW, that means that all these three need to be together. So that's 2 factorial. And so my answer is 6 factorial minus 5 factorial plus 5 factorial plus 4 factorial plus 4 factorial plus 3 factorial plus 3 factorial minus 2 factorial. And that's that for problem 1. Any questions on that one? All right. So problem 2 was the one about the degree sequences. So for both of them, I can use the degree sequence theorem. If you check the basic stuff for the degree sequence in part A, everything works out. So you need to look for something else. So you can start using the degree sequence algorithm. 1, 2, 3, 4, 5. I'm missing a 2. 6, right? 4 2s. So I'm subtract from the next 6 elements. I subtract 1, so 5, 4, 4, 1, 1, 1, 2. I reorder 5, 4, 4, 2, 1, 1, 1, and then I keep going. So 1, 2, 3, 4, 5. I remove that 5. subtract 5 from each of the next 5 elements. I reorder, and then I keep going. So I remove the 3, I subtract 1 from each of the next 3, I reorder, I don't need here. And this one is not the degree sequence of a simple graph. That one would need to have one point with degree 2, one vertex with degree 2, and the others with no edges. But that's not a simple graph. It has a loop. Okay. And then for part B, we do the same thing with this other degree sequence, 6, 6, 5, 5, 3, 3, 3, 3. We remove the 6. We subtract 1, 2, 3, 4, 5, 6 from the next 6. 5, 4, 4, 2, 2, 2, 3. Reorder 5, 4, 4, 3, 2, 2. Did I miss something? 5, 4, 4, 3, 2, 2, 2. Okay. Then I remove the 5, subtract from the next 5 elements. So 3, 3, 2, 1, 1, 2. Reorder 3, 3, 2, 2, 1, 1. Remove the 3, 1, 2, 3. So this is 2, 1, 1, 1, 1. You can even go further. Remove the 2, subtract from these 2, that's 0, 0, 1, 1. So that's 1, 1, 0, 0 when you reorder. So whatever stage where you can actually draw the graph, you can get started. So this one is 4 versus the 2 of degree 1. So there you go. And then we go back. And so we're going to look at this one right here. So we're supposed to add one vertex that's attached to the 2 ones, right? So I'm subtracting, to the 2 zeros. I'm subtracting from, these are the ones that I subtracted from, so it's supposed to be attached to the zeros in my previous stage. So now I'm gonna have that vertex that has degree 2 that's attached to the zeros. And then we look at the next stage, that's that 3 that we remove. And that vertex is supposed to be attached to a 2, 1, 1, a vertex of degree 2 and 2 vertices of degree 1 in the previous stage. So that's my new vertex. It's going to have degree 3. It's attached to a 2, so this one, and any 2 vertices of degree 1. So here you actually have different choices. I'm going to choose these ones. But it could go to any of these 4. Choose 2 of these 4, and it will still work because all of them had degree 1 in the previous state. And then I go to the previous one, that's this 5. And then that one is supposed to go to 2 3s, a 2, and 2 1s in the previous stage. 2 3s. So here, there's only 2 vertices of degree 3 so far, this one and that one. So it needs to go to those for sure. So it goes to 2 3s. To a 2, you have 2 choices, this one or that one. Just pick one. And to 2 1s. So those need to be this one and that one. And then the last vertex, it's a degree 6 vertex that is attached to a vertex of degree 5, 4, 4, 2, 2, 2 in the previous stage. So that's the only vertex of degree 5. Then we need 2 4s. Here's one of degree 4. And here's another one of degree 4. And then 3 2s. So here's one of degree 2. Here's another one of degree 2, and here's another one of degree 2. So I'm just going to join this to those. To this one, to this one, to that one. And there's your graph. Yeah. Okay. So questions for that one?
Oh, so that's what it meant for that problem. I wasn't sure exactly what it was asking for, so I kind of just skipped part A, and part B I drew the graph, but not like that.
Okay, I'll take a look, Sean.
But yeah, I was like, I remembered you talking about this, but I didn't really have a firm understanding on how to do that properly yet.
Okay, I'll take a look, Sean. Then we can go over the exam in my.
But at least now I know. I learned now, so at least if the final exam's cumulative, then I can maybe remember this part.
Yeah. So when the exam is ready, as you know, I know you go to my office hours regularly, so we can go over it. All right.
Yeah, I was going to say I missed the rearrangement step, but I still got a final graph that worked.
Okay, that's fine.
Yeah, you'll see it.
I'll see it. Yeah. I'm just asking you to draw a graph. So if you only found the graph, that's going to give you partial credit. You still need to do this part for the first, to take care of the first part of the problem, right? So you need to do this. If you cannot reconstruct it from the algorithm, that's fine, as long as your graph has that degree sequence. So it's not mandatory to use the backwards, procedure to create it. If you create one, that's fine. That will give you the points for drawing the graph. Okay.
I used the algorithm, but yeah, just the same thing. Like it missed the step, but yeah, just okay. We'll figure.
It gets very crowded. And sometimes you're trying to draw the graph in a way that looks prettier, I guess, or clearer, and then that's actually pretty hard. So I myself make a lot of mistakes while I'm trying to reconstruct it. So that's why I try to use colors and just kind of leave it as it is. And as you can see, I kind of try to place my vertices like at a different level so that I know which ones start from which stage and all that. But it takes practice. It can get a bit messy. But if you are lucky and you can find your graph with that degree sequence, that's enough. Of course, for that second part. Okay, so for problem 3, it has these 3 parts. The first one, you will need an isomorphism. So what I usually do is I try to identify like key components of one of my graphs and then try to identify them in the other. So this graph is actually pretty similar to one that we had in class, if not exactly the same. The other one, I think it's a little bit different. So I'm going to get started with those 2 C4s. And those are kind of matched by these edges. Right? So I'm going to use this. It doesn't have to be like that. Okay, solutions can vary. But just because my green edges, like that C4 is self-crossing in the left, I'm going to try that one as my green C4. I'm going to try the outer square as my other C4. And so, I'm trying to come up with all the other edges are supposed to be connecting my 2 cycles. And I'm trying to just make sure that my labels work out. As we were doing in class, sometimes you start your labeling and it doesn't work, so maybe you need to change it a little bit. Okay, so I'm going to start with, this is going to be my A. No, this one I'm going to make my A so that it looks more similar. It's almost like I take the green one and rotate it. So I'm going to do A, B, F, E. Precisely, if I rotate my green on this first figure, 90 degrees this way. So I have here my A, B, F, E, A, B, F, E, and back to it. And then I'm going to label the other So we have these red edges, and I know what the red edges are on the left. So I'm gonna label the other ends of those red edges. So for example, this one is A to something. Here it's A to H. So this one is H. And then this is B. B goes to C with a red edge. So B goes to C. That's C. And then E goes to D. E goes to D. And then F goes to G. So this one is supposed to be. And I still have to verify that these labels for the blue cycle are in the correct order. So H, C, D, G, H, C, D, G. So it works. That's my isomorphism. Sometimes, because my initial labeling of the green one was arbitrary, maybe I should have used that as A and then get started from there. A, B, C, D. I mean A, B, F, E. So maybe that relabeling. If at the end my blue cycle doesn't match, in this case it did work. But if it doesn't match, then you can try starting with a different labeling of the green one and see if it works out. So this time it works, so we're done. That's the isomorphism. Again, there are different answers. It is not the only one. Okay. So the second problem, the second and third parts, you have to prove that the graphs are not isomorphic. Where's my other part? Did I erase it? Where did my other part go? Maybe it's behind something. Oh, here it is. Okay. So for parts B and C, I need to show that the graphs are not isomorphic. So for the first one, we're using complementary graphs. So I'm going to draw the complement on top of this with a different color. You can also draw it in a separated space. But I'm just going to draw it with a different color. So every edge that's not here, any two pairs that are not connected, originally connected, I connect with the other color. So from that vertex is those two, from this vertex is those two, from that vertex is this two, from this vertex I'm missing this one, and I think that's it. Just to make sure that I have everything, you're supposed to have 6 edges around each vertex. So I have 4 black ones and 2 red from each one. Mm-hmm. So that's together, the red and the black graph are the complete graph with 7 vertices. Mm-hmm. And then I can do the same I'm going to do the same in the other to get the complement. So from each vertex, I look at the pairs that are missing. So that's there. I'm missing this one. That's there. I'm missing that one. And I'm missing this one. So I'm missing this. And I'm missing this.
That's disappointing. I just realized for 3A, I don't think I even submitted my answer because I think I got lost in some piles of paperwork with scratch paper. My bad.
Don't stress out, Sean. Wait until we actually have the results, okay?
I just let you know that I feel guilty now.
It's all right. Don't worry. Wait. So for each of the vertices, I check what's missing. So let's see, what am I missing? What else am I missing here?
They connect to the left to right.
Left to right. Yeah. Well,
to the middle.
Let me label them and you can tell me. Maybe. So what am I missing?
6 to the middle and 3 to the middle.
Oh, thank you. Yeah, I don't have the 7, huh? Thanks. There you go.
Yeah, it's funny. I missed the 2 to 5 and 4 to 1. So.
All right. So now we're going to see what those complements are. Remember that we did one where we were trying to see because all the red graphs have degree 2, then they're unions of cycles. And so we're going to see what unions these are. So what you can do is you can, I guess, go over the edges, choose a point to get started and follow it. Like 1, 2, 3, 4, 5, 6, 7. So I actually got the full start. I'll do it again. I return to the original point. Okay, so here we go. So I start here. I go 1, 2, 3, 4, 5, 6, 7. So it's a full cycle. This is C7. Okay, and then I'm gonna try to do the same thing on the other one. So pick a point to get started. I guess I'll start at 1 and I start walking on some direction. So 1, 2, 3, 4. So that's a C4. And I return to the original point. So that's one connected component. So I have C4. And then I have another connected component. So pick your starting point and walk in any direction you want. You go here. This is your only exit. This is your only exit. That's a C3. Because the complements are not isomorphic. Actually, you can see one has 2 components and the other one has 1 component, connected component. So this one has 2 connected components. Complement has 2 connected components. But here the complement is connected. So 1 connected component. So the complements are not isomorphic. Therefore, the graphs are not isomorphic. So that's for that one. And then for the last one, you have to prove that one of the graphs is bipartite and the other one isn't. For the bipartite one, the first one is bipartite, the second one isn't. So for the first one, we start coloring. That's 1. And then everything that's adjacent, and I'm going to record like what order I'm following. This it's not necessary for the one that's bipartite, but it is for the other one. So that's my first vertex I color. Then this one's everything that's attached to it needs to be the other color. So I'm gonna label those as 2. That was what I color in my second stage. And then everything that is attached to those. Actually, you know what? Let me do in any order. I color 2, 3, and 4. And then in the next stage, I color every time I need to color a vertex that's attached, that's adjacent to one that's already colored. So, for example, I can color that one because it's adjacent to these 2, and these are blue, so that one has to be red. So that was my 5th vertex I color. And then I can color this one because that one is adjacent to 5. So I can actually color it. Oops. So that's 6. And then I can color this one right here. That was the 7th that I colored. And then this is going to be 8. It's adjacent to only blue ones. So that needs to be red. So this coloring shows that the graph is bipartite. You can double check that every edge has both colors. So it actually looks like blue on one side and red on the other. Mm-hmm. And then to show that
it with numbers.
No, the numbers are not important here, but they are important when you prove that that a graph is not bipartite if we want to do it by showing that the coloring is not working. The easiest way to prove that the graph is not bipartite is by showing that there is an odd cycle. The graph is not bipartite is by showing it's not working. The easiest way to prove that the graph is not bipartite is by showing. Sorry, was this Elizabeth? I couldn't understand what you were saying. Were you talking about the first graph? This first graph, the one that we just finished?
No, I think it was Amber. Sorry.
Oh, thank you. Amber?
Sorry, I didn't say anything other than the numbers, but you said no.
Oh yeah, the numbers, when it happens to be bipartite, the numbers are not important. Because to show that a graph is bipartite, the coloring is enough. As long as this happens, that every single edge has different colors, that's enough. You don't need the numbers. If you want to use it for your proof, so let me do this. I'm going to do this in two ways. If you want to show that the graph is not bipartite, then you need to show that your moves were forced, and therefore the numbers are important there. Now, the easiest way to show that the graph is not bipartite is just by showing an odd cycle. If you find an odd cycle, it's not bipartite. So that's the easiest way. Here, I don't know if you see a smaller cycle, but you can see, for example, there are plenty. But this one is C5. I'm not sure. I don't think that this one has triangles, which will be the smallest possible odd cycle. So once you show that C5, it's an odd cycle. So not bipartite. That's the easiest way. No labeling, no numbering, no nothing. That's the easiest way. Okay. If you want to go with the labeling and the graph is not bipartite, then the numbering that I was trying to do here, it's actually important because you need to show that you were forced in every single step to have that coloring. Mm-hmm. So the first vertex can be any color you want. You're not losing any generality. So that's one. And then force moves are caused by coloring something that's already attached to a color vertex. So what I mean is that this needs to be blue if the coloring is forced to be blue, if the coloring is working, right? So this one is forced to be blue, this one is forced to be blue, this one is forced to be blue. Make sense? That's why the order is important. You need to show that you are forcing your moves. And the order is not unique either, and the starting point is not unique. Mm-hmm. But it needs to be a force move. Mm-hmm. So another force move here could be this one, for example, because that one is already attached to blue vertices. So the only way for me to know that it was, it was actually a force move is to kind of follow a certain order. Then this will be your contradiction, right? That would be like the fifth vertex that you looked at. It has no possibility. Everything was forced. Right? That's very important because otherwise, you're going to start coloring arbitrarily, and even in the one that was bipartite, you will eventually get a contradiction, and that doesn't mean that the coloring doesn't exist. Mm-hmm. So that's my contradiction. I don't have if it's red, then I have an edge that has this one will have 2 red endpoints. If it's blue, this one will have 2 blue endpoints. Just to make my point, you could even, if I start with, and I copy this one. Yeah. So if I start with this one that now I know it's bipartite, right? but I'm not careful with with forcing my moves. It's this one, right? So if I'm not careful forcing my moves, I can say, okay, that one, I didn't lose any generality. Just to show you why it's important to have some order while you're coloring. And then I can say, okay, and this one I'm going to make it blue because I want to. There, I'm losing generality. So I'm just going to say this is not forced.
Yeah, I just thought that was like assumed when we were coloring, is like, or obviously because it's like you have to connect blue to red, so I thought that was just part of the process.
Yeah, exactly. So it needs to be first moves because you see, if I do this, then
but like I didn't think to label it because of that. Like I thought it was kind of like implied.
But then there's no way to know how you actually got to that contradiction, right? So, for example, here I could do this and say, "Oh, contradiction," not bipartite.
Oh, you're saying that we had to label them?
If you're showing the coloring, if you're using this coloring method to show that it's not bipartite, you need to show the order in which you color.
With the
That's
color,
why I'm
right?
saying
just coloring, right?
When it is bipartite, the coloring is enough. No need for ordering, the coloring. But when it's not bipartite, you either give you could use your coloring with no explanation and then see that you're getting a contradiction. That means that there must be an odd cycle, and then you find it. So this is like the easy, shortest proof that you could have. Just show me the odd cycle, nothing else. But if you're planning on using the coloring argument to show that it is not bipartite, then you need to show the order in which you color.
How about we label as a red and blue?
What do you mean? Like writing?
Yeah, like red. Yeah, like red and blue. Yes, yes.
Yeah, that's fine. That's fine. Yeah.
Oh, but since we have to prove that one is not bipartite, you had to put the numbers. That's what you're saying, right?
Yeah. So to show that this one is bipartite, the coloring is enough.
For office hours, I remember getting help from you with one of these problems similar, and we went through it, and we were using different colors, and I don't think we use numbers. That's why I'm just double checking with you.
No, but we're explaining, right? The thing is that when we do it in person, you can say, look, this one could be any color. So what do we color next? Or that one, or then that one, or then that one. But when you just write it in paper for somebody else to see later, then how do you know in which order it was done? Right?
Oh, okay. I see what you mean.
So, and this is my example of why it is important to do it in some order. If you were to do something like this, it seems like your conclusion is that the graph is not bipartite, but it is bipartite, right? So so I can say here, maybe let me see if I can move this. So this coloring does not work to show that the graph is not bipartite. And again, this one is actually bipartite. So let me say this graph.
Do we still get like partial points or no?
Yeah, I need to see exactly what's there. Sometimes it's very clear what we're doing. I don't know, like different people point to different things and different ways. So, but yeah. Okay, so this coloring does more to show that the graph is not bipartite. It actually is, just to make sure. But the reason why, because the moves, no, the colors were not forced. Makes sense? Now, in this one, every move was forced. As you can see, every time that we color a point is because it's forced to be that color because it was already, that vertex was already adjacent to a vertex that was colored, and therefore the move was forced. Mm-hmm. Right. So, but the truth is that what you usually do is you try to get your coloring started. When you get to a contradiction, it gives you an idea. So it tells you, first of all, if everything was forced, it tells you that the graph is not bipartite, and therefore there must be an odd cycle. So what you do is you find that odd cycle, and that's your proof. Yeah. Okay. Any questions? I guess I'll put this into different pages later.
Yeah, I just have to wait for my score now. Thank you.
Yeah,
thank you for going over the exam.
No problem. I always try to give as much partial credit as possible. I just need to see, the details for each one. So please don't get discouraged if you see something that doesn't look exactly like yours. It's probably completely correct, and it just, the answers to any of these can be slightly different and still be correct.
Yeah, pretty.
How many points is
the rule?
Did you say?
Gomez, sorry, can you repeat?
Points you said 105 from the exam?
Yeah, so the score is out of 100, so you can think of having like 5 extra points. So if you get 100, anything between 100 and 105, that's like more than 100%, right? So 100% or more, you have those extra 5 points. So if you get 80 points, that's 80%. Even though 80 out of 105 is less than 80%, if you get 80 points, that's 80%.
For exam 3, do you think we should review this stuff still go back and practice on this section?
You'll see what is needed for the new topics. Remember that we really don't have a cumulative final exam. The final exam covers the new material, and for the new material, we're going to have sections H of both books. And, for those, you're going to need some of the previous stuff, some of the, like from the entire semester. We're going to talk about isomorphic graphs. So you need to know what it means and all that. But I won't ask you questions. I will only ask you questions about those 2 sections. It's not cumulative.
Oh, okay.
So once we go over the 2 sections that we're missing, then you'll see what are the things, maybe concepts or things that we did before that are used for the new material. Those are the ones that you will need to review, but not necessarily.
Oh, yes. Section H from the graph theory book and the combinatorics one, both of them?
Yeah, both of them. H in both. A coincidence. Okay. Yeah. So remember, final exam is not cumulative. It's really more of a third midterm.
Okay, thank you.
Okay. All right. So I guess any other questions? All right. So I'll get started with section H of the graph theory book. It's shorter and easier. And then we'll finish the semester with section H of the combinatorics book. That one is a little, in my opinion, a little harder than the graph theory one and a little longer. So let me get started with this one. So it will be section H in graph theory. its planarity, planar graphs. Okay, so we know that any graph can be drawn in many different ways. For example, K4 can be drawn in many ways, but in particular with crossings, like this, like the square with its diagonals. K4 just means 4 vertices every pair is joined by an edge, or without crossings. That would be like a triangle with a vertex inside. That's still K4. Mm-hmm. However, not every graph can be drawn without crossings. So, for example, we'll prove this. Like the smaller examples are K33 and K5. So K33 is, two, maybe I'll do it, like, it's bipartite. So you have like 2 parts. Maybe I'll make it a little bit bigger. You have 2 parts, and then every vertex on one part goes, or is adjacent to every vertex on the other part. So of course that's one drawing with crossings, but you cannot make it without crossings. And K5, it's just 5 vertices where every pair is joined by an edge. Every pair is adjacent. So that's K5. These 2 graphs cannot be drawn without crossings. Proving this is not trivial. But at least you can try, So I can try making K5, K5, for example, I can say, oh, let me get this started with these. I'm going to try to avoid now I can draw the pentagon outside, and then I can start drawing like the star, right? But then I need to go from this vertex to that vertex, and I don't want an intersection, so I can maybe go this way, and then I need to go from this vertex to that vertex without an intersection, so I cannot go inside because then I will have a crossing, so I can probably go this way, but I still need to join this vertex to that vertex, and I won't be able to join them together without a crossing. If I kind of go this way, I will create that crossing there. If I go outside, I will create a crossing here. Or if I go outside like this, I still create a crossing there, and maybe a crossing here. So if you try to join those 2 together, that edge will create a crossing no matter what. Now, this is still not a proof unless, again, everything was forced in my argument. The way that I did it, I'll explain later, so we'll write it as a proof. But same as with my example for the bipartite graphs, this is not a proof unless everything was forced, because maybe if it wasn't forced, maybe I just didn't make the right choices at any given minute, at every given time when I was drawing the graph. And maybe it is still, possible to do it with no crossings. So this is just trying. We'll prove it later. Okay, so a graph that can be drawn without crossings is a planar graph. So that's a definition. So planar graph is a graph that can be drawn with no crossings. So any cycle is planar. Cn is planar for any n. Cn is just a cycle with n vertices. We show that K4 is planar. Here we have a picture that has no crossings. K23 is planar. You just have to find a drawing where you don't have any crossings. And so here I'll say to prove that the graph is planar, just be a plane drawing. So a planar graph is the graph itself, even if it's drawn with crossings. If you can change the drawing so that it doesn't have crossings, then it's planar. A plane drawing or a plane diagram is the actual drawing without the crossings. So K23 is planar. Even if it's drawn with crossings, you can say it's planar. Mm-hmm. So here there is a drawing of K23. Because we can draw it with no crossings. So here I can draw 1, 2, 3. That's A, B, C, let's say A, B, C. And then I can have C and D, C on one side, D on the other. And now A and C are joined together. A, B, O, no, C, D. Let me make this one D. I already had a C. So E is joined to ABC, and D is joined to ABC. And now I don't have any crossings. Mm-hmm. So these are isomorphic. I actually gave you the isomorphism. You don't actually need to give, well, that's the isomorphism, but the idea is that both are drawings of K23. And as long as you can show me one drawing that has no crossings, then the graph is planar. So for K4, the drawing, we had it earlier. And for Cn, you can just draw the regular polygon. Okay? So that's a planar graph. Now, a few other concepts that we're going to need is a tree is a tree is a connected graph with no cycles. So, they're not always drawn like this, but they're like branches of a tree. That's why they are called trees. So that's a tree. There are no cycles. And then a forest is a graph with no cycles. It doesn't have to be connected. So it is actually the union of trees. So it could be something like this. So this is a forest with 3 components.
Can you explain the definition of a planar graph again? Because I'm trying to take notes and pay attention at the same time.
Planar graph just means that you can draw it with no crossings.
And it doesn't matter how we draw it as long as we have like the right amount of vertices, right? Or
as long as you have the right graph. Mm-hmm. So many times, so I can give you an example of what type of exercises you can have. Let's see. Let's do it here. So let's do H1. Actually, let me go to a different page. We'll do H1. I'll come back to that one. So if you look at your book, problem H1 gives you 3 different graphs, and it's asking you to prove that they are planar. The first one looks like this: 1, 2, 3, like 3 squares with their diagonals. This looks like that. So, of course, this one has crossings, so that's not a plain drawing. But if I want to prove that this graph is planar, I need to draw an isomorphic copy of it that has no crossings. So look, I can try to start drawing it. So I guess I'll have my three squares like that. So far so good. But then when I start, these are not isomorphic, right? I need to make an isomorphic copy. So it needs to be those 3 squares with the diagonals. However, if I draw this one, for example, then I cannot draw that one because then I have a crossing. But I just need to make sure that those 2 vertices are joined by an edge in order to have an isomorphic copy. So instead of joining them like that, I can join them like this.
But there can still be one crossing inside the squares then.
I need to draw it with no crossings whatsoever. So, for example, I'm missing those 2 diagonals. I can draw one of them there, but the other one, I cannot draw it here because then it wouldn't be a plain drawing. I need a plain drawing.
But we can still keep one diagonal?
Why not? Do you see any crossings so far?
Oh, okay.
So these are the crossings. These are the crossings right there. That's what I cannot have in my drawing. Mm-hmm. As long as I don't have any crossings, yes, I can have diagonal. Right. Mm-hmm. But you see, now I cannot draw this one because I will create a crossing right there. But I still need to make sure that those 2 vertices are joined to each other by an edge. So I can kind of imagine that the edges are made of, like a rubber band, so I can kind of pull that diagonal and just make it go around.
I thought a crossing was I thought you said a crossing was a vertex in the middle of the graph. Or did I misinterpret an earlier graph?
This is a crossing.
Oh, okay. I thought I saw like in a previous slide, it showed a vertex inside like the middle of the graph.
No.
I guess I imagined it. Never mind.
Yeah. So.
Oh, there it is. That's the one I was thinking of. The triangle one.
No crossings here. Imagine that the edges are straight. Whether they cross or not, it's just the definition of something crossing. Intersections, let's say. So that's a crossing. Here I have 3 crossings. I want to avoid them.
So if there's a vertex where the lines intersect, then that's not considered a crossing.
That's not a vertex, remember, Sean? Those are not vertices. The vertices.
Right. So if you were to put a vertex there, then it wouldn't be considered a crossing, right?
Exactly. If you have vertices there, then the drawing is planar.
Okay.
But because we don't have vertices there, then we need to get rid of those crossings. So you have to reroute the edges. Mm-hmm. So same thing here, maybe. Yeah.
So the graph that you draw in A, like the first one, so that it's not a plane diagram, but it's still a planar graph because you can write a graph without crossings, right?
Yeah, very important. So this is not a plane diagram, but planar, because that one, right? We can draw it like this. So here's what I'm trying to do, right? So here I have one of the diagonals. I cannot have the other like that because I will have a crossing. So I'm just gonna kind of pull that as if it were a rubber band and just go around. I still need to make sure. And so what this means is that these 2 copies. When I say because we can draw it without crossings, so draw an isomorphic copy. So they still need to be isomorphic, essentially the same graphs. Mm-hmm. And I didn't give the labels, but you can see that it really is the same graph. I'm just pulling that edge, this edge, and this edge. I'm just kind of pulling them to go around and avoid the crossings. Mm-hmm. And if you wanted to give an isomorphism, it's very clear what the isomorphism is. It's just that.
Yeah, it's a bit clear now.
Mm-hmm. Mm-hmm. Okay. So you can try parts B and C in H1. See if you have any questions next time. Those are, same idea. They give you 2 other graphs and they ask you to prove that they're planar. So try to reroute the edges so that you avoid crossings. So showing that something is planar is easier than showing that something is not planar, because showing that something is not planar, you need to make sure that none of the infinitely many ways that you can plane, any of the infinitely many ways that you can draw it will have at least one crossing. And how can you deal with that infinite number, right? So showing that something is planar is relatively easier than showing that something is not planar. So I'm just going to say here, to prove that requires an argument. And it's not, no, it requires an argument and in general than proving that something is planar. So to give you an idea of something you can do to prove that a graph is not planar, we are going to start with, so this is with the graph in H4. Like this. It has 6 vertices. 1, 2, 3, 4, 5, 6. And then looks like this. And it's actually labeled A, B, C, D, E, and F. Those are my vertices. Okay. So this one is planar, but it's not as easy, I guess, to find. You can try finding the plane drawing. This one I think is harder than the ones in problem H1. Mm-hmm. So one way that you can use, one way to show so I guess one technique that usually works is to start with a Hamiltonian cycle. So a Hamiltonian cycle is a cycle that uses each vertex exactly once. Okay, so here I'm gonna try to find one. That's the first problem. But here I can pick one. So I'm gonna go like this: 1, 2, 3, 4, 5, 6. That's a Hamiltonian cycle. Okay. Now, because I want to draw my graph with no crossings, that cycle cannot self-cross in my new drawing. Mm-hmm. So that's a Hamiltonian cycle. In a plane drawing, the cycle cannot self-cross. So it really needs to be, this one is a C6, 6 vertices. So it really needs to look like this. I mean, not necessarily like a regular polygon, but it needs to be, kind of go around. You cannot twist it. Mm-hmm.
So you started with, I have a question.
So yeah.
For the first one, for the cycle, that you started with A, right? With the point A.
Yeah, it doesn't matter where you start. You just need to visit all the vertices exactly once.
Oh, okay.
But you see, in my new copy of the graph, I cannot have crossings, right? So that cycle cannot self-intersect. So it actually has to go kind of around in a circle. So it needs to be like this. All right. So now, which edges am I missing? The missing edges are AC, BF, and D. So this one's right here. That one, this one, and that one. Those are the three edges that I'm missing. Mm-hmm. And so this technique can be used to show that something is planar or not. Look, I find my Hamiltonian cycle. I know that it has to look like that. It cannot self-intersect. So all the vertices need to go around. So I draw that Hamiltonian cycle. Now I look at the edges that are missing, and each edge needs to be completely inside or completely outside of that cycle. And that's because we don't want to have crossings, right? The first one that you add, you don't lose any generality by assuming that the first one is inside. And that's because, you can imagine that you've seen in other classes that the plane is essentially, if you add the point to infinity, it's essentially like the sphere. So the interior of this hexagon, if you imagine it on top of a balloon, the interior of this hexagon can become the exterior if you kind of make that hexagon go around the balloon, if you stretch the balloon, or if you punch it in a different way to make it planar. So you don't lose any generality by assuming that AC, for example, is inside. So you can assume without loss of generality that AC is inside. Then you can try to draw BF. BF could be inside or outside. I will lose generality. But the thing is that here, it doesn't really matter if I lose generality. This one is going to be planar. So, I can draw them in any order. It's like the bipartite case that I showed you before. Just as long as you get your plane drawing, you don't have to explain how you got it. So here's BF. And then BE cannot go inside. I just draw it outside. Here's my plane drawing with plane diagram. And we're done. Okay, but this is kind of an organized general way that you can try and draw. Now, again, this technique can be used in general, and you can use it for H5, for example, to prove that a graph is not planar. So I'm going to ask you to try the same technique with K33. And we get this, we'll start from here next time. K33 is not planar. So you won't be able to draw a plane drawing. But we're working towards an argument that proves that it is not planar. And we're going to use this technique for that. Okay? So get started with K3. Find a Hamiltonian cycle here. So that's going to be your task for the weekend. So that's K33. Find a Hamiltonian cycle. Draw the vertex, draw it as, that's going to be a C6 as well. Draw it as I did here. See which edges you're missing. You again will be missing 3 edges, and convince yourself, try to come up with an argument why you cannot draw those 3 edges without crossings. Okay? So try it for next time. We'll start here next time. All right? Thank you, guys. I'll see you Tuesday. Have a nice weekend.
Thank you, Professor.
I recommend you to go through the sections, see, read it in advance. We'll finish it on Tuesday.
All right, sounds good. Thank you.
Bye, everyone.